Merhaba arkadaşlar. We are going to continue the discussion on recursive programming. So last time, if you remember, we explained how you can write a recursive program. Mainly, if you recall, any recursive program is written in the way that you basically call the method itself by going in a recursive manner, calling itself over and over. And reaching to a base level where you actually stop the recursion. So this was the main idea. You always will have to have a base case where you're going to stop the execution of the recursion, and then also you'll need to have the iterative step which recursively calls itself again and again, right? So this is basically the two things that you have to have in any recursive program. The code of a recursive method must be structured to handle both the base case and the recursive case, as we said earlier. If you don't have the base case, you're gonna never stop, and you will just run forever, which will probably stop by either memory, out of memory error, or some sort of error in your execution until resources are finished, and you don't have any more resource to utilize in the environment. So it's basically, if you call a method itself over and over, let's say A is calling itself again and again without a base case, what's going to happen is that it is going to continue forever. However, this is going to at some point will need to stop, because with each invocation of your method A, you're basically allocating a memory space for this in the heap, which is basically the area for method calls to operate on. And call stack will create, all these method calls and allocate space for each one of these local variables, and then, instance variables, whatever is needed for each method. You're going to allocate a memory space for the method call, and after some point, you'll reach to the end where you won't have any space available in the operating system, which will generate the termination for the application. However, this all depends on what kind of method you have, how much space you have, and things like those. So in order to prevent that, you'd like to have the base case and use that for stopping the recursion at the end. So when you finish the method call, obviously you return back to the caller of the original method, which might be the same method name as we did with the recursive implementation. So this was the example, the basic example, which sums up numbers from 1 to n that we covered last time. And if you recall, in the recursive step, what we have is we call the same method with the same name. However, we have a different argument than the original case. And in the base case, as shown here, you stop the execution whenever this number reaches 1. Obviously, this is going to be reached because every time we're decrementing our sum value by 1, so that at the end, if the number value is positive, it is going to definitely, reach to an end by reaching to this endpoint in the recursion. However, obviously, if you think of this example, can you consider any case this may not end at all? If number, for example, starts with 0, that's going to cause a problem, and you're not going to stop because there's no condition checking for that. Or also, like the value 0, if you have a negative value, right, the stopping condition is not there, which will again go forever if you do not consider that problem, right? So you would like to include in your implementation such problems if you're going to write a pure, safe method for negative or positive values.
But when the num get to 1 and this return 1. Hocam bu result'a herhalde
Yes, for the final value, if you run it with sum 1, it is going to return result equals 1 and then return this result. So the question is how this is working, or the problem with the negative values? No, it doesn't return 1 in any case. It will, let's say I have a call such as sum 5. Okay, so how is this going to run? It will come, number is not equal to 1, and then it will say result equals num plus, which is 5, plus sum 4. So then it's going to call sum 4, which is going to be equal to 4 plus sum 3, right? And then it will call 3 plus sum 2. And then the last thing that it is going to see is 2 plus sum 1. If you look into this, whenever it comes to sum 1, if num is equal to 1, result equals 1, and then you return result. So basically, this will return 1, right? And then you get the result value for sum 2. 2 plus 1, 3, result equals 3, and then return result, right? So it's going to return this result after that as 3. And then it will compute 3 plus whatever is the result of this sum 2, which is 3. It will get result equals 3 plus 3, 6. And then return result. Each method invocation has its own number value. So for example, this sum 5 has its own num value, and then this one has its own num value. So they are not the common parameters that they are using. In each method invocation, as I said earlier, so you will have sum 5 method call here, where it has its own local variable as num equals 5. Anything else as an argument, nothing else but except result. So it has its own num and result values. And then whenever you call the next time sum 4, it is going to basically have its own values. Number equals 4, and then it has its own result value stored separately. And then whenever you call sum 3, it will have its own number value, which is 3, and then result is initially not initialized. And you will continue in this fashion, so that whenever you're done with, let's say, sum 2, number is equal to 2, and then result. And you have the last call, which is sum 1, number equals 1. And then within this method, this is the last call to the sum. You will have if num equals 1, result will be equal to 1. So this will have result equals 1. And after it comes to the return statement, it will return by returning the result, which will return 1. And then you will deallocate the memory space that is reserved for this specific method. Now, this result will then be computed by getting the number plus whatever is returned is 1. 2 plus 1, it is going to be 3. And then this will return 3 as a result, and the allocated space will be deallocated for this method call. And for this one also, 3 plus 3, you'll get 6 for the result. And then it will return 6. And you will get rid of this. And you will have result equals 10 here. And then you will get rid of this. And the 10 will be returned. And when you come here, you'll get result equals 5, the number plus the sum of 4, which is returned to be as 10. And then you'll return that, which is going to be 15, and then this will also be over and returning the final result at the end. Okay? So basically each method is a separate instance. So they do not, mix one to another. This is important. If you feel like they have the same name, however, they are totally separate instances of the same method. So you're reserving a space for each method separately. And that's why if you call this 1,000 times in a recursive manner, what's going to happen is that you'll have a stack of these methods, called one after the other one, which is going to cause a lot of memory consumption. Also, going here and coming back is also additional, overhead that is included with the recursion. So if it is not really providing much benefit to do it in using recursion, you may prefer not to use it at all. Okay, such as this example, it's obviously a lot easier to do it in different ways. So you probably want to not use it in implementing the sum of the terms that's from 1 to n. Okay, any question? So as I said earlier, note that just because we can use recursion to solve a problem doesn't mean we should. So you should look at the problem specifically and see if recursion makes sense and if it provides an elegant solution. Otherwise, you want to use a iterative version of the same problem, probably. So as I said earlier, indirect recursion, we mentioned that. So if you are not calling the same method, but you're calling method A calls B and then B calls A, it is in a cyclic fashion and calls itself over and over by using the internal method B. This is called indirect recursion. However, it bears the same problems or same nice features provided with the recursion. However, with indirect recursion, you have additional complexity that is caused by calling this and returning back to the same method, which may complicate the debugging of the code. So you probably don't want to go into this indirect recursion most of the time. So we did that. In recursion, so we have done the maze traversal. I'm not going to go into that again. You can check that code again. If you look into the Towers of Hanoi problem, this is basically a very common problem in computer science, and there are a lot of algorithms that is being developed to solve the problem. However, the feature that recursion provides is really elegant for this specific problem, and that's why it is one of the common examples that's shown with recursion. So basically, Towers of Hanoi tells you that anybody knows Towers of Hanoi, by the way? So it's basically you have pegs and you have disks that you would like to locate disks on the pegs in the order of their sizes. So if you, let's say, have a peg that is something like this, and then you have disks that are in 3 different sizes, and you'd like to move these disks onto the second peg. Can you do it without violating the rule that bigger cannot be on top of a smaller one? Can you move these from here to there without violating the rule? Rule is that always smaller is on the top. If a bigger disk is there, that needs to be on the bottom of the pile. So in this case, you're not going to be able to do it in any way, because you need to have a temporary location to move the disks to in order to use, right? So that's basically, you need to have the third peg to do that. What you would do in normal implementation is that if you happen to play, you will first move this small disk here, right? And then you'll get rid of this. And then what are you going to do? You'll basically move this disk to here so that you have it there. And then, let's say this is my temp, and then this is my final. What am I going to do next? Then I will just move this disk to final. And then I will move this one from here to there. And then I will move this small disk from here to there. And next thing is I'm going to move from here to there. And then I will move this one from here to this. This is final, this is temp. Okay? If you want to do it the other way around, if you want to make this final, obviously you'll just start with, instead of this one, you'll start with this one. Okay, so this is the Towers of Hanoi problem, and then, the goal is to move all the disks from one peg to another under the following rules. The rules are, we can move only one disk at a time, and then we cannot move a larger disk on top of a smaller disk. And if you see the problem, so this is the original configuration. And then whenever you have the first move, you just move the small disk to one of the pegs, and then you move the medium one onto the other peg, as you see. And then you get back this smaller thing on top of the medium one, and move the big one onto the final position as shown here. And then next thing is you move this small thing back from middle to the left one. And then next thing is basically, you know the idea, you get the idea. So at the end you're done with the order of pegs. So if you have 4 disks, how are you going to do? 5 disks, 6 disks. So it's basically actually doing the same thing. Whatever you're doing for 3 disks is same as for 7 disks. Only the only difference is that you have to apply this over and over to move disks from one location to the other one for each subset of the disk configurations. Okay. So if you have 4 disks, what you're going to do is basically you'll ignore this disk and then you will try to move these as a whole into, let's say, this is your final position, okay, and then this is temp. So what basically you're going to do is that you will take the top 3 as you did before from here to there. That's the first thing. And then this is the first move. And then you will take this to the final destination of this. And then take this as a whole back on top of this whole thing again. If you have 5 disks, same thing. You'll do whatever you did with the 4 disk. You're going to take the top 4 and move it as a whole piece and then get it back to wherever it needs to go. Okay? So that's where recursion comes into play. So you use how you did implement 3 disks on the towers of Hanoi when you're implementing 4 disks. When you're doing 5 disks, you use it as if you order 4 disks as a 1 disk block and then get the 1 disk to its correct position, the biggest one. And then whenever you need to do the 4 disks, what you do is that you get 3 disks as a whole big block, put them as one, and then get 1 disk at the end to correct position. And again, for 3 disks, you consider it as to be 2 disks and plus 1 disk. So this is exactly what we do with recursion. Okay? And if you look into the code, solve towers of Hanoi. So as you see, towers of Hanoi, private int total disks. So this is the instance variable for the towers of Hanoi. And then as you see, it constructs the object towers of Hanoi with the number of disks that you would like to create, and that's basic. And this is the solve method, which is basically the starting point for the towers of Hanoi solve problem. And if you call the solve, it basically gives the total disks, right? And then it gives the source where you start the disks at, and then the target, and you also give the peg that you're using for temporary movements. So this is the source and this is destination, and then you're using the second tower for the movement, or peg for the movement of the disks. And if you look into the move tower method, basically this is start and end. If you look into the move tower, basically what you do is that this is a recursive call. So you have the base case, int number of disks is equal to 1. If you're only trying to move 1 disk, you basically move 1 disk start and end. So you just basically move the disk that is from the starting location to the end location. This is simple. So you're just moving 1 disk at 1 movement. And then, however, if you have more than 1 disk, in that case what you do, you go move tower number of disks minus 1 start, temp, and end. So you basically use get rid of the pile that I mentioned, the 3 disks in this example, and you start and take them to the temp position. So this is the final target of the 3 disks, okay? And you start at temp and then use end as if your temporary position holder. And then what you do is you move the 1 disk from start to end, and move tower, you move the remaining ones from the temp position to the end. So let me show this on the board, that will make it more clear. So let's say this is the 4 disk combination that we have, and this is start, and basically this is the temp for the original call, and then you have end. So what you do is if number of disks is equal to 1, in the initial case it's not equal to 1, it's equal to 4, and you will go into the else part. What does it do? It tells you move tower number of disks -1 start to temp. So basically it is calling that, hey, I would like to get rid of these 3 disks. In the original case, if you remember, number of disks is 4. So -1, we are calling this with 3 disks, and I'd like to move this 3 disk combination from start to temp. So I'd like to use this temp to get rid of this from top of this biggest disk, right? So what am I going to do? I will go from start to temp. However, I'd like to use this end disk as my temporary disk. So what's going to happen is that it will basically move this 3 disk pile to the temp position after I call this move tower. And then the next thing I will do is that move 1 disk start end. Since all this pile is gone now, what I will do is that I will move this only remaining disk from start to the end. Okay? I moved. The next thing that I need to do is that I will need to have this pile moved on top of the biggest disk, which is going to basically do it by move tower number of disks -1, move it with 3 disks. However, the starting point is temp, which is exactly where they are right now. And then they are going to go into the end tower, which is this one. And in the meanwhile, in the process, this was already empty, so I can use this peg to move to use as a temporary, which indicates the temporary peg for my movement. So it basically is going to move this pile from here to there by this second call. Obviously, whenever you call this, right, whenever you have this move tower with 3 disks, it's going to have its own internal implementation. How are you going to implement that? It's basically going to divide this into, remember this was 3 disk pile. It will call in an, again, recursive fashion, right? So it will have these 2 disks at 1, and then it will consider these 2 disks and 1 disk alone. Then what's gonna happen? You'll just move this from here to where? Which disk am I going to use? So I will move them to the start, because there you have the biggest disk which you can move on top. And then I will move this from here to there, right? And then I will just get the remaining disks on top of the thing. So it's basically recursively calling itself over and over with smaller number of disks. And again, the base case is if you have only 1 disk, you're just going to move the disk from the starting point to the end. Okay? Any question? If you want to do it in an iterative fashion, it is also doable. You can write any recursive methods iterative version as well. There's no problem. You can write that. But when compared with this, implementation, it's a lot complicated. And in terms of number of lines of code, you will have more lines to express the same problem. However, the advantage is elegance that is provided with only 3 method calls, which is, which also comes with the overhead of calling multiple methods over and over. So move 1 disk is basically, system out print line. So it just prints out on the screen which disk is moved from which location to where. So it basically indicates the movement of 1 disk. And if you look at the solve towers, basically it shows you near towers of Hanoi and then towers solve, so that you call it with, the number of disks that you would like to execute. So as you see, it indicates the order of operations that you need to perform. Move 1 disk from 1 to 2, move 1 disk from 1 to 3, and so on. So it indicates all the operations associated with the Hanoi problem. So if you happen to decide to use, let's say, 10, what do you think is going to happen? Obviously, since it's calling in a recursive fashion, it is going to have many iterations to go through. So if you wanted to write it by hand, it would be really hard to implement this, right? So it provides, a nice solution for the towers of Hanoi problem. Any question? What do you mean by counter? I mean, you can keep track of a counter by calling the method. For example, in this case, basically you are calling itself over and over, right? And you're going in a tree-like structure, so you can have the level of the depth of the tree, but the only way to do is, I think, if you use a static counter to keep track of the number of method calls. That's the only way to do it. So if you have a static counter to keep track of the number of calls, you can do that. Other than that, if you want to have, if you want to know the depth of the calls, you can use a variable that's passed as an argument to indicate what's the level of the method that's called. Also, you can get that from the problem size, tower size. In this case, 10. It is going to go all the way to depth 10. And we'll come back from there, right? Any question? So, returning back to the recursion topics. So if you look into the recursion in graphics, this is also useful. It really provides nice visual concepts. So for example, if you would like to display images in a mosaic form, which means like, let's say you like to use the space that's provided for you in the applet into 4 quadrants. So basically what you have is, let's say I have a screen that I'd like to divide into 4 equal parts, right? And then on each one of them I display an image here, there, and this one. And then for this part, I do the same thing by dividing it into 4 equal quadrants and use this part for the smaller images with the same image. So this is going to be same as this one, this is going to be same as this one, and then this is going to be same as this one. And then again, you will have, in a recursive manner, you will divide it into smaller squares over and over into 4 equal quadrants. Upper left quadrant repeats pattern, so you basically repeat the same pattern until you reach to a certain level. Obviously, you need to have a base case where you stop. In this case, it's probably a pixel or the size of the image or the length of the square that you're using and so on and so forth. So you can choose the corresponding proper certain size that you would like to stop. And the tiled pictures.java does that. So let's see. If you look into the example, this is the applet. So you have the world image, and then you have the Everest image, and then you have the goat image on the top right corner. And then as you see, the pattern is repeated here. So you have smaller images, same things. You have even smaller, and then continues like that. As you see, it stops here. There's no smaller circle, smaller square that is divided into quadrants. And that's where the stopping condition actually have been reached. So if you look into the tiled pictures.java, so it uses the JApplet, and tiled picture extends JApplet. You give the height and width of the applet, and then you have the minimum size that you would like to stop, right? So from that point on, if your image is smaller than that, you're not going to continue from that point on. And you create the images that are world, Everest, and goat by getting them using the document base, which is basically providing the current folder, and then you have the world.gif and all the GIF images that are associated with those images, and you set the size of the applet with the given width and height. So this is basically then going to draw these images page onto the page, and you have the size given as an argument. So it's going to basically paint the image Everest onto the location X. This is the X dimension. And then this is the Y dimension coordinates. And you have the sizes in terms of X and Y. So basically, it is going to get the current coordinates, such as the size and size, right? So you start with the first picture on the coordinate that is given as this point. How are you going to get that? The size is given with, for Everest, sorry, this is going to be this one. For Everest, X is going to be, if this is your coordinate system, X and Y, original coordinate is 0, 0. So you'd like to get a 0 plus size over 2, which indicates this point to start with, right? And then you will have the dimensions of the image by size over 2 here, and then size over 2 here. And for the second image, you have the goat, which starts with size over 2. So this is going to be the starting point. And then size over 2 is the x coordinate. So this is the x dimension. And then for the y, since it's with the original coordinate system, it will be size over 2 by 0, which indicates the starting point. And then these again are going to show the sizes of the images. And then the third image is obviously going to start with this point, which is size over 2 and size over 2 in terms of coordinates, x and y. And then sizes are again size over 2, size over 2. So next time whenever you call this, you basically give the size half of the original size, and every time it goes into the correct location to print things onto this scale. So next time whenever you call, if size is greater than minimum, so if it is greater than 20, what are you going to do? You'll call the draw pictures method recursively to go onto a smaller half of the size and paint things onto the same page. Okay? So basically, what is the stopping condition in the recursion here? So size actually prevents going forever. So if you get a size that is less than 20, it's not going to call itself and it will stop, which indicates the base case in which you just leave things out and do not continue further on. So this is the tiled pictures example. Fractals, this is also a really nice graphical implementation, and there are various forms of fractals. And if you look into the fractal concept, it's a geometric shape made up of the same pattern repeated in different sizes and orientations. So you do the same thing over and over. However, you add an angle, you change the size, you select a different point, and things like those create the fractals. The Koch Snowflake is a particular fractal that begins with an equilateral triangle. So basically what you do is that you take the triangle with 3 points and then recursively call itself over and over by creating additional points. How it does this is that basically it uses the coordinate that is 1/3 of the two points for this line, for example. It takes this point and then creates an image something like this. So this is going to be this side, okay? And then similarly you get a point here and then another point. And with an equal length, you go this way and generate this sign. And then again, you divide this into 3 halves, 1/3, and then you generate this structure, which is again another equilateral triangle. So as you see, if you go further on, what you're going to do is that you'll create the same thing for this one. So you will have this, and then generate this. Same thing here. You'll generate that, right? And then you'll do the same thing here. You'll have this. And same thing. So if you go further on, you're going to do the same thing over and over, which I probably won't be able to do it here. But if you go until a certain pixel or size for that, such that you need to stop somewhere, right? You need to stop it at a point. And if you go below a certain size, here you will stop it, and otherwise it will continue in a recursive fashion, which creates a snowflake type of, screen or image on your implementation. So if you would like to get a higher order of the fractal, you'll get each line of each edge of the triangle replaced with an angled line segment, as I shown here. Koch Snowflake.java. So let me show you that. If If you look into this, this again extends applet, japplet, and implements action listener. And the most important thing is that you have the applet size and everything, and you have the min and max values set to 1 to 9. And you have, if you look into here, that's where things actually happen. So you have the new panel, you create a box layout on the x-axis, and then you set the preferred size, background is yellow. And also I have here the images increase.gif and increase press.gif, which basically increase the size and decrease the size as well. And you have here, let me show you where actually you add those decrease and increase buttons. And if you look into here, there must be another file with this, Koch panel.java. So if you look into the Koch panel.java, this is where things actually happen. Sorry. And if you look into this, Koch panel int current order, it's going to set the background to black, and then current equals current order. When you come to the draw fractal, you have the main method that is creating the edges for the fractal. So it basically has the order, which indicates what's the current order of the fractal, and then you have the x and y coordinates, and then x5 and y5, which indicate the points on the line segment, and then you had the delta x and delta y, and also other, temporary variables. If order is equal to 1, so you have reached the lowest order, what are you going to do in the lowest case? You'll basically draw a single line, right? So this is the base case. In this case, base is this, so you'll just draw the line. However, if it's not the base case, what are you going to do? You'll get the distance between the endpoints. So you'll call, let's say these are the 2 points, initial triangle, right? So what you will do is that you'll first get the delta x and delta y distance between the endpoints. So you'll get just the distance between these 2 points. So let's say this is a 90 degrees angle. And then you get the delta x and delta y in terms of those 2 points. And then you get the 1/3 of the points by getting x1 plus delta x divided by 3. And then y1 plus delta y divided by 3, such that you get this point, right? And then similarly, so if I get 1/3 of the x and 1/3 of the y, right, I'll be able to get the same point that is on the same line, however 1/3 of the distance from the beginning point. And then the next point that you have is same thing, however just the 2 other third points, sorry, this is the other points that you have x4 and y4, is basically this point. Okay, so you get the 2/3 delta x, 2/3 x1, delta y, 2/3 y1, right? And you get the other 2 points here. So you get this point and this point, and then you need another point, which is this one, right? So basically the formulation to get that is x1 plus x5 divided by 2, and then square root of SQ. What was SQ? It's not square root. SQ is the math square root 3 divided by 6, which is set to a specific value here. So it is used to calculate the third point, and then if you calculate the third point's x and y coordinates, what are you going to do next? Now I have my original points, right? So this is x1, y1, this is x5, y5, right? And this is x2, y2, x4, y4, and then this is x3, y3. So I got all these 5 points. This was the original points given, and then I generated these 3 points by only using the math. And then what am I going to do next? I will just draw the lines for these, right? So I'm going to basically draw the necessary lines. So as you see, it is going to call the new draw fractal by doing that. Draw fractal order -1, and then it gives the starting point x1, y1, x2, y2. So you gave the draw fractal to these 2 points to generate a new fractal. And then you also call these 2 points to generate a new fractal, these 2 points to generate a new fractal, and then these 2 points to generate a new fractal. So that's why I have 3 different draw fractals. If the order is reached to 1 in any of these, it's basically going to draw the first case, it's going to draw the lines. However, if they have not reached the order first, then it's going to do it over again to create, using these 2 points, it will generate the other remaining points and then redo the same thing. Okay? Any question? You look like you didn't understand. Did you understand? So basically, draw fractal calls itself over and over using the 2 points. The 2 points are the start and end. By looking at these points, if your order is 1, so you have reached the final condition, in that case you'll draw a line. However, if you have not reached the final case, order equals 1, what you're going to do, you're going to basically create those points, which is easy to, get with math. You get these additional 3 points, and then you call the draw fractal using these 2 points as a new draw fractal. So it's going to basically do the same thing on these. And then also you'll do the same thing for these 2 points, and then these 2 points and these 2 points. Okay, so that's what exactly we do. So we initially started with the triangle. We called the fractals of each line, and then within each line we created again another fractal, and we continued in that fashion. So if you look into the code, it may be more clear for you to understand if you look into the implementation. So basically, you have the x5, y5, and x1, y1. You basically get the new points. And then if you would like to draw a triangle, you'll basically continue and get the next order of fractals as you go. So if you increase the order, you'll get more and more, smaller pieces on each edge of the Koch snowflake. So if you look into the chapter summary, basically what we covered is that the recursion in general and how to use recursion in graphics objects and also in general programming assignments. So I'd like to do more recursion examples. To start with, if you would like to, let's say, if you would like to find the minimum, so I'd like to write a method find min, which is going to basically take an array as an argument, integer array, and then will return me the minimum in a recursive fashion. We didn't do it last time, right? So let's say I have a public int find min, and then I have an int array a. So these are important. Also, when we were grading the exam, I saw that you didn't even understand what are the returning, what you need to return, what you will take as an argument. That are primitive things. If you don't know that, you won't be able to solve the problem at all. So you have to understand it takes an integer array as an argument. Then I will have an integer array a as an argument. It returns an integer as a result. Then the returning value should be an int, right? So you will have those ready at the beginning, even before implementing the method. So if you're asked to find the minimum in a given array, how are you going to proceed? And let's say in this case you need to have an additional argument to this. Let's say we would like to add another argument because it will make life easier. Int start. Okay, so we are going to compare the current minimum let's say I have the array, right? And then I will start with the first element. And I will compare this one with the minimum of this part. So how can I do that? So I will say if what's the base case? If start is equal to what? A dot length minus 1. Why do I check this? A dot length minus 1, right? So that shows me I have reached to the end of the array. Then what am I going to do? Return if I reach to the end, what does it mean? What is the minimum in the last element? There's only one element. So it's the element that is minimum, right? So I will say A start. So if I reach to the end of the list, right? If this is the last element, and if this is my starting point, which is equal to the length minus 1, then I have reached to the last element. Let's say this is 5. I know that this is the only element, so that must be the minimum of the list, which is itself. Right? Else, what am I going to say? So you can write a 3-operand comparison operator. How can you write that? Return how am I going to get the minimum one if I compare with the current value? So if you consider the first element, I will compare this with the rest of the remaining elements, right? So I'm going to return A start less than A start less than what? Find min, and then I will have the A as an argument, and then what will I have? Start minus 1, start plus 1. And what am I going to return? If this is true, question mark. If this is true, I will say A start. Otherwise, find min A start plus 1. Anything problematic? So if I have reached to the end of the list, then this must be the case. If start is equal to A dot length minus 1, this must be the case. Otherwise, I have one more element, which means I'm here, and then I have start plus 1 that is available to compare. Any question? Start minus 1, you mean start minus 1? If you go start minus 1, this one? It's the same thing. If this is smaller, you'll select this one, whatever is returned from this part. If this is smaller, you'll get that part. Obviously, you don't want to call it twice. You can call it beforehand and then use that as a variable and use it. For example, something like else, you will have something here. A equals find min, and then A start plus 1, and then you use here A instead. If A start is less than A, then A start or A. So what does this help you to do? It helps you to get rid of 2 calls for the find min. Why? As I said earlier, this is going to prevent that. If you have reached the start, that means that's the last element. In which case you won't go into that else part. Okay? All right, let's give a break and we will continue.